Everybody, and thank you all for coming out on this very chilly Saturday morning. And hello to the Zoom folks, which I can't see, but I assume you're out there. Okay, this morning we're going to talk about basically two topics and how they intersect. We're going to talk a little bit about ham radio. We're going to talk a little bit about 3D printing, and we're going to talk a little bit about why 3D printing and ham radio go together like peanut butter and jelly. Well, I feel like peanut butter and jelly. A lot of you guys know me. I'm Mike, N2HTT. Been licensed, I think, for 26 years. I couldn't do the math. It's been a while, 1987. And I have a small 3D printing business that I've been running for the last 2.5 years. I will talk a little bit about that, but not too much, as that's not what this is about. However, you can reach me at n2htt.mike@gmail. You can take a look at my blog, n2htt.radio. And if you want to check out the accessories that I make, it's http://hamgear3d.com. Don't worry about taking notes, because all of this is going to be available on a resource page. I have the link at the end. You'll be able to get links to the stuff that I talk about, presentation, this video, all sorts of stuff. Okay, what is 3D printing? Okay, Wikipedia says that it's an additive manufacturing process. It means instead of starting with a block of stuff and taking away material to get what you want, you add material and build up to what you want. So there's some advantages to additive manufacturing, and one of them is you don't have waste, right? You machine something out of a solid block of aluminum, you get your product and a big pile of shavings you have to do something with. Okay, for hobby purposes, we're going to talk about basically two kinds of 3D printing, and then we're going to talk about one kind of 3D printing. Stereolithography, which is referred to as SLA, and some of you may have heard of this or seen pictures of it or seen it, uses a bath of plastic resin that is cured with ultraviolet light. And they shoot ultraviolet light through the resin to the spot where they want solid material and gradually raise the printed object out of the bath. So it kind of emerges from this bath of resin. The other kind, the kind that we're going to focus on this morning, is called fused deposition modeling, or FDM. And that's where we take plastic filament like this, and we push it through a heated element, and it melts, and then we put that melted material where we want it. So the way I like to describe FDM is if you can imagine a very precise, computer-controlled hot glue gun moving in 3 dimensions. That's FDM. Okay. Both methods build up these objects in layers. So we need to take the object we're looking to produce and slice it into layers, and then we're going to go around and we're going to extrude plastic for the FDM approach until we build up to the solid object we're looking for. Okay, I anticipated my next slide, so we already talked about this. SLA is liquid resin, more expensive raw material. It's more difficult handling. Okay, you have something that's basically a toxic material. It's epoxy resin. You have a machine that has to be filled. There's more cleaning issues. There's fumes. It's better suited to a dedicated workspace. I wouldn't want an SLA printer in my family room. Just it's not really appropriate for that. But a lot of people love resin printing because it's potentially gives you finer detail. You can make those layers very, very small, and you can get a finished product that has a finer surface. FDM uses relatively inexpensive solid plastic filament. This is a spool that would hold a kilogram, 2.2 pounds of plastic. costing anywhere from $15 to $25. And you can do an awful lot of projects with a kilogram of filament. This goes a long way. I'm not going to say that it's totally concern-free, but you can use one of these printers in your home with a lot less concern. There is a possibility for producing volatiles, you know, because you heat up plastic, you get a little volatile material, microparticles, that kind of thing. But the risk is extremely low with FDM. So I wouldn't worry about having one of these in my family room. So that's just my personal thing. So anyway, for the remainder of the talk, we're going to talk about FDM because I don't use SLA, and I'm not that knowledgeable about it. Okay, thanks, Lou. Okay, now, putting this together, I was trying to have a logical flow, and we're going to go into some detail right now. Let's talk about the filament, the material that's used for FDM printers. This stuff, which I'm holding in my hand, is called PLA, polylactic. Oh, good, thank you. Sorry, I keep drifting off the sweet spot here. This is called polylactic acid. It's a great printing material. It's easy to print. It's forgiving. It's non-toxic. It has good strength and impact resistance. It's actually made from corn. So it's not, but it's not biodegradable. That's an important point. In this form, it's not biodegradable. And because it has a relatively low melting point, it's not suitable for applications above 140 degrees Fahrenheit. Now you might say, all right, I don't usually hang out in Death Valley. That's not going to be a problem. But on a nice hot summer day with the windows rolled up, the dashboard of your car might hit that temperature. So I use this for ham radio applications, many, but I am mindful of that temperature limit. Okay. If you look at the specs for your rig, you may discover that they don't recommend operating your equipment at 140 degrees Fahrenheit either, so probably not too much of a concern. The other popular home printing material, which I don't have an example to show you here, is a plastic called PETG. I'm not going to try and remember it, polyesyl terpolate, something like that. It's the stuff that plastic water bottles are made out of, okay? Modified with glycol to make it a little well-behaved for the melting process. It's slightly more difficult to print, to get your printer tuned into it. It's non-toxic. It has good strength and impact resistance. It has better heat resistance. You can go up another 20 degrees Fahrenheit. So there are those who say PETG is better because of that additional heat resistance. Okay, let's go on to the next one. All right, two other filaments that you may run across. ABS. This is the same stuff that your car bumpers are made out of. Okay, it's a really tough plastic. It's difficult to print. It's prone to warping and temperature variation. Typically, if you're going to do that, you want to have some kind of enclosure around your printer to keep the drafts away because it'll warp. It's toxic fumes, so that's not something you want to do in the house. You want to do that out in the studio. But has excellent strength and impact resistance and excellent heat resistance. So if you're doing something where you have a demanding, you have a concern with temperature, or you have a demanding structural part you're trying to make, ABS is a good choice. But probably for hobbyists, not so much. Specialty filaments. They make filaments plastic infused with wood, with metal, carbon fiber. They make flexible filaments that let you print something that's a little spongy, like a cork in a bottle type of thing. They are difficult to print. And they also, depending on what's included in them, can be rough on the printer. There's additional wear on the printer. So that kind of stuff is basically if you have a design requirement that you need it, or you have an aesthetic requirement, they make shiny filaments that look like metal. They're all plastic, but they have like a shine to them. If you have that need, then they're appropriate. Probably not so much for a ham radio application, though, unless you like shiny accessories. Let's go on. Who's going to get his exercise this morning? Okay, so what's involved in making a 3D print? The first thing you need to do is you need a design. You need to have, in a computer modeling program, a description of the 3D object that you're trying to create. Okay, we're going to talk about what kinds of software there's available to do this. There's a little snapshot of the design, which is this, right? Okay, once you have your design, your drawing, your 3D drawing of the object, you need to convert it into instructions that the printer can understand. Okay, the printer has, in its control board, has firmware that knows how to interpret. You can't see it too clearly on the slide, but it's actually a bunch of commands. It says move here, extrude a little bit, move there, extrude a little bit. And the general term for those instructions, that machine language, if you will, that the printer understands, is called G-code. Okay, so we'll use that term again in this talk, but G-code. So you have to have a program that takes a 3D drawing, a CAD drawing, and turns it into G-code for your printer. Okay, step 2. Step 3, you have to get those instructions to the printer so that the printer's firmware can interpret it and create the object. And I don't have any with me, but there's a picture. You guys have all seen SD cards and micro SD cards. You're familiar with that from your phones, right? So typically you would copy the G-code file onto an SD card and put the SD card into the printer. There's a little slot over here. And then the printer will read that and operate from that, from those instructions. Alternatively, you can have a dedicated computer connection to the 3D printer, and those are the names of some programs that are popular that are used to control 3D printers, where you can, from the computer, say, okay, take this file, send it to the 3D printer. Printer will do that. Computer's giving you a status as to what's going on. God bless you. So there you go. Those are the steps. Let's move on. Okay. And the 3 kinds of software you would need. Okay, 3D modeling software to create a design. Most, how do I say this? Most 3D modeling software starts with the idea that you make a 2D drawing of something, and then you push it into the 3rd dimension. It's just called making a sketch and then extruding the sketch. Okay, and there's a whole bunch of these. A very popular, powerful, and lovely one that's extremely expensive is called Autodesk Fusion 360. But there are also free ones, like something called OpenSCAD, something called FreeCAD, and they all work with this idea that you make a drawing and push it into 3 dimensions. There's a learning curve with these, I'll be honest with you, and it takes a little practice with them to be able to get to do what you need to do. I got started with Autodesk because I took an online course, which I'll talk about later. And if you take an online course, take the right online course, they'll give you a free subscription for a couple of years to Autodesk, and you can learn how to use that. And it's a valuable skill. Another thing which is very popular, it's a free program. My son uses it. It's called Blender. It's really not designed for 3D modeling in the sense of making objects to be 3D printed, but you can use it. I don't, so I can't tell you too much about it, but it is out there, and it's one of the options. That also, I think, has a fairly steep learning curve. The last one I want to tell you about, and this is really good. I love Tinkercad. Tinkercad is a web-hosted software. So the only thing you need to use, the only thing you need to be able to use Tinkercad is a web browser and an internet connection. Okay. Tinkercad is provided by Autodesk. And it's there trying to get people hooked into doing 3D modeling. They make this available for free. Tinkercad works differently than these other two. Tinkercad gives you a menu of 3D objects. Here's a sphere, here's a cylinder, here's a cube, here's a triangle, prism, just an assortment of shapes. And you build up what you want to make by combining these shapes. And the shapes can be made negative space too. So you can take a cylinder and make it a hole and put the hole in. Sounds a little cumbersome maybe, but the learning curve is low. With a little practice, you can get quite easy, facile with it. It's easy to learn. And it is actually a very powerful modeling tool. And in fact, all of the designs that I do, maybe not all of them, the key was done in AutoCAD, but everything else was done in Tinkercad. And you can see a little, this was a tripod topper for a vertical antenna, that orange thing. And that was all modeled in Tinkercad. So I recommend, if you're interested in learning 3D modeling, Tinkercad is a great tool, and I urge you to try it out. And again, all you need is a web browser, and you can experiment with it. Okay, now let's talk about the next piece of software that you need to use the 3D printer, which is a thing called a slicer. Okay, remember, we're starting with a 3D drawing of an object, and we want to get to the point of layers, right? So the software that makes the layers, called a slicer. There's a ton of them out there. There are free programs, Cura, and Slicer, spelled cleverly with a 3 instead of an E. And I never know how to pronounce that. It's called Slicer. And then there are programs that are made by 3D printing manufacturers, printer manufacturers. Prusa makes a slicer, Matter Control. So once you get a 3D printer, you will probably get a link to the manufacturer's program, and then these other programs are out there. And as you learn it, you may choose one or the other. It's all, matter of preference. The final piece of software that we need is actually built into the printer, and that's the printer firmware. You can see there I got a shot of this little screen down here, and that's your user interface. There's an encoder and a button, and you basically select items off a menu to control the printer. The printer firmware can be provided by the manufacturer. Usually when you get your printer, you're going to get an SD card, or it's going to be already flashed on the control board. And there's also community-supported firmware. If you get into it to that level, you can build your own firmware. And the advantage of that is when you build your own firmware, you can control a lot of the parameters that you might choose to do. And again, we're going to stay on the surface here, and I'm going to drill down into a level of detail that will make everybody fall asleep. But once you get into 3D printing and you learn a little bit about it, you may find that, gee, I really want my printer to work slightly differently than the manufacturer's firmware, and that's how you do it. All right, so let's take a look at what the parts of the 3D printer are. Okay. You will always have some kind of rigid frame, right? And that frame is going to support the print head. It's going to keep everything in square. This is the basis for the geometry of the printer. Okay. You tell me if I'm doing something out of frame or... No, that's good. Okay. Man, this is regrettably a dead printer. It needs repair. And so this is not currently functioning. That happens a lot. Okay. You're going to have a power supply. Power supply is going to provide all of the energy necessary to move the motors, melt the plastic. Typically, these guys idle at about 30 watts, and when you're melting plastic and pushing it out there, you might be up at around 300 watts. So think, while you're printing enthusiastically, think 300-watt light bulb. Okay. Here, turn around this way. Okay. Underneath here, you see we have a whole bunch of cabling going to the control board. I don't know if you can really see the control board in there. The control board's a little microprocessor, either an 8-bit or 32-bit microprocessor. And it does a number of jobs. It controls the motors, which we'll talk about in a moment. It provides, it controls the heat provided to the bed, the heat provided to the hot end, the thing that melts the plastic to push it out, and controls various fans, and gives you the little user interface that you see on the little screen. So this is, this machine, by the way, it's a bit of a checkered past. I believe the heater on the bed shorted and it destroyed the control board. So this one needs a fair bit of maintenance before it comes back. Okay, let's go to the next slide. That's my cheat sheet, is what we're going to talk about. Okay, the next thing we got to worry about is moving this thing around. So let's talk about geometry for a minute. This printer and many of the printers, I would say the predominance of the hobby printers that you're going to see use an XYZ geometry. So in those layers, we're moving in the X and Y, right? And then we have a way to move in the Z direction, and that gives us our third dimension. How many here have ever played with an Etch-a-Sketch? Yeah, all right. So Etch-a-Sketch, XY, and move your Etch-a-Sketch up, that's your Z. Okay, so that's what's going on with that. That motion is provided by a number of what are called stepper motors. I guess this is probably the best one to look at right here. A stepper motor is a motor that can be controlled by a microcomputer, and you can move it a tiny little bit in either direction. So if the motor is here, then I want to go over there, I can say, okay, I want you to move 100 steps this way, and it'll zip and stop. Okay, so it maintains a notion of where it is, its position, and it can go back and forth. So this stepper motor controls the X. Okay, this would be the X-axis moving across the gantry here. There's a stepper motor in the back. Okay, and these are all the same except for the one for the extruder. But that stepper motor controls in this machine the bed, which moves back and forth. That's your Y. And there's a stepper motor. This machine's not standard. I've modified this a little bit. So on this machine, we have two stepper motors, one here and one here. They're attached to a lead screw. And as they turn, the lead screw pushes that gantry up and down, and that's your Z-axis. This model, when you buy it from Creality, only has one lead screw. And I added the second one. It didn't help. Okay. Not an endorsement. And then finally, we have a stepper motor here that drives the extruder. Now, the extruder is an interesting piece of equipment. It's this little thing right here. And basically, there's a gear and a spring and a roller. And the roller is pressing the filament against that gear. So as that gear turns, it will push the filament either towards the hot end, where it's going to melt, or pull it away. All right, so it's a very simple design. It's just a motor, gear, and spring. There's I don't know if you can see that, but there's a fairly stiff spring there. And that's the extruder. Now we get to some of the interesting stuff. Sorry. This whole assembly here is called the hot end. When your filament filament comes down through this tube that guides it to the block. Okay, there's a little block here that gets really, really hot. And sometimes you forget that and try to do something, and it reminds you that it gets really, really hot. Yeah, you learn not to do that after a while. That block is provided electricity by these two fat wires, and that's what heats up the filament and causes it to melt. And we're talking temperatures of about 220 degrees centigrade. So that's like, or Celsius, 220 Celsius, so it's roughly 400, 425 Fahrenheit. That's hot. Don't touch the block. Okay. And the filament is coming down into the block, and you don't want the filament to melt before it reaches the block, because then it's going to get all jammed up in here, which is one of the exciting things you learn to deal with over time. So we have this very interesting looking fin thing, and that's just a heat sink that allows you to waft away the heat so that the filament doesn't melt until it reaches that block. And inside the housing here, I don't know if you can see it, but there's a fan here, and that fan's blowing all the time on this heat sink. And the net effect of this is you just want that stuff to melt just when it hits the block, not before, and that's all controlled with that fan. There are also fans on here that blow down on the work, and that's used so that when you deposit that layer of plastic, that fan blows on it and cools it so it sets right away, so that when you come back around to do the next layer, it's hardened. Okay, so that's the hot end. Okay, there's another device here, which I think we'll talk about in a minute. Okay, let's go on to the next slide. Okay, so basic printing tasks, and then we'll talk about that thing. When you get your machine, it will probably need some calibration, and the manufacturer tells you what to do. They give you instructions, and basically what you're telling it is, you know, how many steps of the motor do you need to push out a millimeter of filament, right? Because when you get your G code and it says push out a millimeter of filament, do so many steps, the firmware needs to know about that stuff. So that's a one-time thing. You do that when you get started. Bed leveling. This is one of the major annoying bugaboos of FDM printing. First off, we're not talking about being level, right? I'm not talking about putting a bubble level on this and making sure that the bubble is centered. That's a nice thing. It's nice to have it level, but that's not really what we're talking about. What we're talking about is, as that little nozzle where the plastic comes out moves around the bed, we want it to have a consistent height, right? Because if it's not consistent, at one point on the bed, that layer is going to be thinner, and at another point it's going to be thicker, and this will be not good. So we talk about bed leveling, but what we really mean is making that travel consistent all over the bed. And there's a bunch of ways to do that. There's manual ways where you move the nozzle to a couple of points and you put a piece of paper there, and I don't know if you can see it. There's these big wheels under here. Is that visible? Probably not. But there's a spring and a wheel, and you can turn that, and it's making a minute change to the bed so that you can dial that in so it's level. The other thing you have, and I think this one's actually broken. It was a casualty when the board got destroyed, is this little probe that comes down. This is under control of the board. It comes down and it pokes the bed, and it takes note of where it gets pushed back up, and it actually measures the height to the bed. And that will go around in a little pattern. It'll jump around 9 times or 16 times and create a map of any irregularities. And then as the printer is printing, it will take that into account, and in the software it will accommodate those little variations in the bed. So that's an auto level, bed leveling. The final thing that's really tricky, and I'm going to just point you to the overhead for this, is the thing called a Z offset. That's the nozzle. That's the place where the plastic comes out. And if I was at 0 millimeters above the bed, that nozzle would be touching the bed, and if I try to push some filament out, where would it go? It's going to push back, and it's not going to come out. And the extruder is going to start going click, 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 click. This is pushing, and it can't go anywhere. So zero height is not really zero height. You have to leave a little bit of a gap for that filament to come out, and that's called the Z offset. And adjusting that is a critical thing that you do in order to get your FDM printer working. And you're always constantly watching that Z offset. Okay, let's move on. Right. So, oh yeah, thank you. You can turn it. I think we're done now with the. Thank you. Okay, good. So if you start 3D printing on your own, you're going to find a lot of material and people talking about the first layer, the importance of the first layer. What's this about? Well, you can actually see a first layer going down on one of the printers there. It is literally the first lines of filament that go down on the print bed. And it's important because if it doesn't stick well to the print bed, chaos will ensue. If it doesn't stick well and your printer's going on doing its thing, eventually there'll be enough torque where the filament is going down to peel the thing off the bed. And then it will start whipping around as it's all dancing in free space and create a nest of plastic. And I don't have a picture of that, but it's not pretty. So you come down, you let it print overnight, you come down in the morning, and instead of your part, you got this bird's nest of plastic everywhere. So it's very important to make sure that that first layer is consistent and it sticks to the bed. If the first layer isn't good, your print is doomed. So there's a lot of mention in the literature about getting a good first layer. So what's involved? The bed material is an important consideration for that. This bed, okay, get it off of here. Come on. There we go. Okay, this print bed is a piece of sheet steel covered with a plastic called PEI, PEI. And it's a thermoplastic that when it gets hot, really likes to stick to the plastics that we extrude. So we warm up the bed. It's got a heater underneath. And this bed material will cause the filament to stick. And when the print's done and it cools off, I just go pop, and it comes right off. Okay. There's many other approaches to this. People print on glass if you want a very smooth first surface, but glass can be hard to get the plastic to stick to. It can be a little problematic to get the piece off the glass, depending on the plastic you're printing. So there's all kinds of possibilities here. Over the course of time, I've come to love PEI print beds, just because they're easy and it works really well. That's not stock. You got to buy that separately. That didn't come with this printer. Okay, and then finally, and then we're going to move on to talk about some other stuff. Rafts and brims. Sometimes your 3D object is very tall. It may not give a lot of surface area to stick to the bed. So you may add some additional material at the bottom that has more surface area so that it sticks. And then your print sticks to that, and then when you're done, you break it off. I didn't mention, but there's also a thing called supports, where if your 3D object has, let's say, an overhang that's hanging out in space, right? Imagine with your hot glue gun trying to draw something in space with nothing to hold it up. So what a support is that it brings material up from the bed, and that material acts as a support. And then when you're done with the print, you break the support material off. Okay, let's go, just hit enter, I think. Okay. All right. How many of you guys have heard of ham radio?
Never.
Never. I'm not going to beat this to death. We just basically wanted to include, for people who are not familiar with ham radio, some of the things that we do. We communicate. We're communicators, and we communicate in a lot of different ways. We participate in public service events and in emergency communications, and we have fun with it.
Want to skip these?
Yeah, yeah, that was a picture of me having fun with it. So anyway, so let's talk about ham radio applications. Ham radio is a great companion to 3D printing because we're always looking for widgets. We're always looking for an accessory. We're looking for a part. We want a coil form, such as Lou was showing you earlier. Ham radio lets you materialize that part physically. You don't have to go out and find a manufacturer of a coil form that's approximately what you want. You can design your own. It's awesome. So what kinds of things can you do with for ham radio? Okay, I brought a few examples here. Antennas are great for, I didn't bring the darn thing. I actually was going to bring that piece to show you. Antennas are great opportunities because we have dipoles that have center insulators. We have end insulators, right? We have end-fed half-wave antennas. You guys use end-fed half-wave? I love it. It's great. Greatest thing since sliced bread. It's just a wire terminated with a little transformer at the radio end. Only one point of support. Very nice for portable. That one happens to be a commercial one that I bought. That was 3D printed, and the guy did a very nice job. He used PET-G, as a matter of fact. But there's tons of designs out there for doing those. Wire winders. You see the two lobes of the thing with the wire around it? That's great. If you make something that has two lobes like this, you make a butterfly. You make a figure 8 around those two lobes, and your wire doesn't get tangled. Whereas when you coil your wire up, you know what happens, right? I'm looking at Joe here. He's familiar with that effect. Coil your wire up, and then you go to pick it up, and it's formed an elaborate knot. That takes half a day to get rid of. Okay, wire yeah, okay. Wire winders. Cases and enclosures. This is great. I could have brought that one too. This is a no-brainer. It's just so easy to make. Am I out of the?
Just put it right.
Am I down here?
Yeah, you got it.
I'm good?
Yeah, nice.
Okay. This was a very complex design that I did early on of a little case for a speaker. Yeah, okay. I was in the, yeah, so you can see that. All right, so I did this in, I did this in Fusion 360 based on how old this is, but yeah, I just needed something. I wanted a little speaker cabinet, so there it is. This was the first 3D printed design that I did, and it's not actually my design. Somebody else, here, I can get it down here? We good?
Big enough, you can see that.
Okay, all right. This is a cabinet for radio. There's actually an HF transceiver in here. And the fellow who did this design put it up on one of the file sharing sites, which we'll talk about in a minute. And he had a design for PET-G that snapped together. And PET-G's flexible, snaps together. PLA, not so much. So I took his design and did what's called a remix. His license for using that design said, you can take my design and improve it, change it, whatever, as long as you post what you do. Kind of like open source. So I took his design and I remade it to be assembled with screws instead of the snap fasteners. So this was the first 3D printed case that I did. And this is really old now. This is about 4 or 5 years old. Okay. Microphones. Here's a little microphone. It's an electret microphone with a switch. You get that in there? We good? Okay. 3D printed case for that. Push to talk. And I mentioned kits. I didn't bring it, but that was a little kit for a low-pass filter that I made a 3D printed case for. That was not my design. That was somebody had published that. And I can't believe I didn't bring one of my rigs today. Hi. You can make nice protective garb for your portable radios. That's what I do in my business. So there's a picture of one of the radios that I make a cover for. Okay, let's. Holders and stands. There's tons of, everybody with an HT, when you sit it on your desk, if you wish you had a little holder for that, right? You do that. Stands for rigs, lift them up, make a little bail for it. And mounting brackets for your car. This is a, I'll bring it over here again. This is a folding clipboard that's designed to hold. I have a little radio that's about the size of a pack of cards, and I just put it on there with the elastics. And I can sit and copy my code, and I've got the radio right there. You see it in the picture. And this folds up for convenient transport. Okay. Yeah. Okay, let's go to the next one. Okay, so let's talk about, you got a 3D printer, you're going to learn how to do some designs, but in the meantime, what if you just want to print some stuff? There are these file sharing sites, and I'm going to mention two here because they're probably the most well known, but there's tons of them. And what this is that people will take a design. I've got designs of mine up on Thingiverse and printables. People will take a design and they'll say, I'm going to put this in, not in the public domain, but I'm going to allow people to use this design. They create what's called a Creative Commons license. And that license may say, you can print this for personal use only. Or it might say, you can print it for any use, commercial or otherwise. Or it might say, not only can you print it, but I invite you to modify it as you see fit. And that's the remix thing that I spoke about before. So you go to these sites and you go in and you can do a search and say ham radio and be inundated by literally thousands of 3D print files that people have put there pertaining to ham radio. There are other sites where people will sell their files, right? So you can go to a file and say, I'm looking for coil forms, and somebody might have a coil form that's for sale. And typically these are not very expensive, a few bucks. And you download the file, put it in your slicer, print it on your machine. Okay. One of my favorite things is this site called yegi.com. And that's actually a 3D printer, a 3D print file search engine. So if I went into yegi.com and typed dipole center, all right, I would find, it would report 3D files, maybe on Thingiverse, maybe on printables, maybe on cults, maybe wherever it came from, a whole list of dipole centers that people had posted files for. And I could choose the one that looked best to me and download the file and slice it and print it. And finally, what if I don't have a 3D printer, but I do want a 3D printed accessory? A lot of these sites will have an affiliated 3D printing service where you can select a file, select a material, and they will print it for you at a cost. And I can't tell you what those costs are because I've got these things. I don't use the service. Anyway, but that is a possibility too. So if you're interested in getting your feet wet with some of this and not getting involved in a printer, that's a possibility. Let's go on to the last one. Okay. Where can you learn about 3D printing? YouTube. Literally, YouTube is the best resource out there. And I would just go into the YouTube search engine and type a question, and you will get hundreds of potential videos to explore, and you can learn a lot. The only thing I would say with YouTube is if you're asking a question, look at more than one answer. Because obviously everybody is an individual, everybody's got their own take on things, and you want to get more of a survey, all right? But YouTube is a fabulous, like if you want to say, oh, my hot end is broken, what do I do? You know, my hot end is clogged. Creality printer hot end is clogged. And you will get a whole list of videos of people showing you how they fix that problem. And among that material, you may find the answer to your problem. So YouTube is fabulous. Of course, you can Google things. Although I find that when you Google stuff for 3D printers, it takes you to YouTube videos. So it's a little incestuous. It kind of takes you around the corner. But anyway, and then finally, if you want a more organized approach to this, there are many, many excellent online courses that you can take, Intro to 3D Printing, that take you through all of this stuff. Some of them are free. Some of them you may have to pay for, but not a lot. I have some links in the resource page for Coursera, which is one aggregator of courses. Udemy is another one, is an aggregator of courses. I think the courses that I took, I forget the college. It was a course given by a college and posted, and I took their series of courses, and that's how I got Autodesk Fusion too. That was part of that, and I don't think I paid for those. I think that was free. Anyway, I'll have a resource page. It's down here. Into htt.radio, Introduction to 3D Printing resource page with dashes. Okay, and on that page you'll find links to all this stuff, this presentation, bunch of other stuff. Okay, I think that's there we go. Questions? Sure. The question is, can you make a Faraday cage with that? What you could do is you could make, remember this is plastic, so it's not. Yes, you can get metal infused plastic. Okay, so you might be printing. You might be able to. It might work. With metal infused plastic, the filament has, I don't know, 20 or 30% powdered metal in the plastic. Is that sufficiently conductive to make a Faraday cage? I don't know. The other approach would be to create maybe a framework with grooves to run wires through, and then wire it up with a copper mesh or something like that. So use the plastic for structural support, and then provide the conductive material to make the Faraday cage. Yes. All right.
Because that's the way your notebook computer is made.
Oh, okay.
Not to radiate. Coated on the inside.
With a conductive paint.
Some sort of conductive coat.
Okay, so that's a good suggestion as well. So you could create a plastic framework and paint it with a conductive paint. And that would give you your necessary conductivity for the Faraday cage. Any other questions?
What does a typical PC look like as far as GPU resources and other resources? In other words, what do you need to have in order to run the printer successfully and to do the AutoCAD software?
Okay, let's break that down. To run the printer, you need virtually no resources whatsoever, because basically you're creating a serial connection to the printer, right? And you're moving files over that serial connection. You're doing and control, you know. So think CAT on your rig, right? CAT control. It's like that. maybe with the moving file. So you don't need a lot of resource to computer control the 3D printer. Okay. To run the CAD software, Tinkercad only requires enough resources to run a browser, because that's the heavy lifting is happening in the cloud. You just have the presentation. Autodesk Fusion has a native install, but it also mostly runs in the cloud. So I've run Autodesk on an old Windows machine, and this is a relatively powerful Linux machine, and I've not noticed any difference between. The other guys, OpenSCAD or FreeCAD, probably require a fair amount of computer power, but I would say that probably any basic Windows laptop could deal with it. All right. The slicers also require some computer power, but on my old Windows machine, running the slicer to convert the 3D image to the instructions could take maybe a minute or two for a complicated design. On this machine, it's, 10 seconds. So, but even on an old pokey Windows machine, I was able to do that without a problem. So I guess the succinct answer to your question, what resources do you need? Any typical laptop, I think, would be adequate to do all of these tasks. Questions? Any other questions? Nobody asked me what printer to buy. Okay. I was going to ask it if nobody else has it. Okay. What you'll find if you survey the market right now, 3D printers got very much less expensive in the last 5 years. And you can find, and there are many good entry-level 3D printers, more than capable of doing the stuff that we've been talking about here today, for around the $200 to $250 price point. Okay? So we're not talking about thousands of dollars anymore. It was at one time, but it's not anymore. Which is the best one? YouTube. Type in, what is the best 3D printer for $200? And you'll have a very pleasant afternoon watching videos. Okay? This machine is a Creality machine. They are notorious or infamous or famous, I don't know what the word is, for being one of the first, a Chinese manufactured machine, and they were among the first that were coming out with the $200 price point printers that were usable, that they weren't junk, and they're not junk. But now there's many, many more. It's quite an open field, but these guys kind of broke the ice on it. Or you can still spend over $1,000 for a hobby printer. Why would you want to do that? Based on my experience, and I'm just going to talk about this really quickly, a machine like this is going to require a lot of hands-on. You're going to get in there and you're going to be changing parts and working with it and clearing jams and doing all that stuff. And you're going to have to, with the inexpensive printers, it might be a little bit of a honeymoon period, but then you're going to be in there under the hood with your hex wrench taking screws off and messing with it. And for people for whom the 3D printing hobby is a hobby, that's the fun part, right? Getting, like we were saying with our radios, we're always messing with our radios and tweaking antennas and doing that stuff. So the entry-level printers are great for that. This past year, I bought an expensive printer because I have, I'm running this business on Etsy and I'm fulfilling orders. And when this guy gets a bellyache and I have to change out the hot end or whatever, I have to spend an hour or two messing with it. I don't want that. I want these things to just be popping off the platen because I've got other things to do. So I bought an expensive printer. Had a great experience with it. It's a printer called a Prusa, by the way. It's a Czech-made printer. I love it. It's a lovely machine. Got over 1,000 hours of continuous print time, and then the hot end failed. So later on today, or tomorrow, I have a replacement hot end to put on the Prusa. But the difference is with the Prusa that during those 1,000 hours of printing, every single print came off the plate consistently. I didn't have to tweak it. I didn't have to fuss with it. There's a 200-hour preventive maintenance that you do that takes about a half an hour, and I did that. It was great. It's trouble-free. And, that's the difference. If you're not worried about that kind of scenario, where you're satisfying an external contract, you're going to get these things out, I think these printers are great. And you'll have a lot of fun with it, and you'll learn a lot, and not spend a lot of money. So that's my take on that. Anything else? Okay, thank you very much. It was my pleasure this morning.